Hello everyone, I'm Farid Al Saad, a PhD candidate at UIUC. In this presentation, I will present our work, Topic Transitions in MOOCs and Analysis Study. This is the agenda of the presentation, and I will start with the introduction and the motivation behind this work. For many decades, the process of creating courses has been a manual task that need to be carefully managed by instructors and experts. With the emergence of massive open online courses, it becomes critical to automate the process of course design to accommodate the heterogeneity of online students and their diverse needs. So currently, the content delivery of a MOOC mimics a typical on-campus organization. However, it presents the idea in shorter chunks and hence fails to accommodate the student with different learning demands, motivations, and goals. Instead of having a set of pre-designed static courses, can we adopt a model in which MOOCs are used as modularized resources to fulfill student diverse needs? So the crucial first step toward developing such a model is the automation of course plan design. So the initial and essential step for automating curriculum planning and course design is to model the relationship between educational topics. And modeling the content structure of MOOCs has recently attracted many research. Most of the current research has focused on modeling the prerequisite relationship. Modeling the prerequisite relations can capture the required concept before learning any concept and hence can help in sequencing educational materials. However, prerequisite relation cannot model the different learning paths accommodated by different courses. So the question is, how can we model the content structure of similar MOOCs in a way that detect the similarities and variations in the learning paths? And in the previous work, we introduced the notion of the precedence graph to model the similarities and variation in the learning paths of different courses. And the precedence graph clusters similar lectures into the same cluster and then link the clusters with a precedence relation that has strength score to determine how this relation is common. In this work, we assume each cluster formed a topic, and a topic is a set of concepts. And hence, similar lectures cover the same topic. The strength score of the precedence relation can capture how likely instructors transit from one topic to another. Therefore, in this work, we generalize the notion of the precedence graph and introduce the topic transition map. Since the topic transition map models the variations of different learning paths followed by different courses, the course is just a path in the topic transition map. And using this representation would facilitate the design of a new course plan as the process becomes a task of identifying a path in the topic transition map. And in this work, we investigate and compare methods to construct the topic transition map and explore how to exploit the topic transition map in sequencing lectures. So we define our problem as follows. Given a set of courses, C, where a course Xi is represented as an ordered list of lecture to leverage the temporal order of lectures or the sequence of lectures. We also assume that the number of topics M is given. Our goal here is to model three things. A, which is the topic transition map, pi, which is the initial probability, and B, which is the topic word distribution. So in addition to the PCK means that we used in our previous work, we explore three more methods: mixture of unigram language model, hidden Markov mixture model, and structural topic model. PCK-mean method is similar, as I said, is similar to our previous work, where each course here is represented as a sequence of lecture, and we first cluster similar lectures from different courses using PCK-means algorithm with some predefined constraint. And we link clusters by using the precedence relations between adjacent lectures and capture the strength of the transition by accumulating the frequency of transition. To find the word distribution of each cluster or topic in the matrix B, we accumulate the vector representation of each lecture that belong to the same cluster. So each cluster here would be a topic. There are also some variation that we incorporate in this work. The first thing is that we model the self-transition between a topic and itself, and we calculate the initial probability of each topic by counting how many times each topic being the first topic in the courses, and then do the normalization. The second method is a mixture of unigram language model, and it is a generative probabilistic model that has been used for document clustering. So to generate a document, we need first to pick a topic, theta, for the lecture, and then generate all the words in the lecture using that topic. The idea here is to use expectation maximization to find topics, which is the matrix B, and here it is theta I, just a vector in this matrix. Then we cluster lectures by choosing the cluster that maximizes the likelihood of the lecture. Finally, we leverage the lecture sequences to find the matrix A and the initial probability pi, similar to the PCK means. The third method is hidden Markov mixture model, which is also a generative probabilistic model that jointly or at the same time learn A, B, and pi. In regular hidden Markov model, as you can see from the top figure, each observation is a symbol, such as a word, that is generated from hidden or latent variable or a topic, and each topic here depends on the previous topic, which is, we call it the Markovian assumption. So to use the hidden Markov model to model the content of MOOCs, we need to update the model as each observation is a lecture, as you can see from the down figure, where lecture here are represented as a bag of words, and each lecture is generated by a topic. To estimate the parameter A, B, and pi, we use a modified version of Baum-Witch algorithm. The fourth model is a structural topic model, STRTM. It has been used by NLP community to model the latent topical structure inside documents by assuming each sentence is generated from a topic. It is similar to hidden Markov mixture model, except that first it assumes a functional topic ZP that capture the general terms or document independent words to filter them out. So each word here can be generated by either the functional topic or one of the content topic. Another difference is that A and B are generated from multinomial distribution, and in the work they use conjugate Dirichlet distribution to impose a prior on them. So for the evaluation, to compare different methods, we conducted quantitative and qualitative evaluation. In the quantitative evaluation, we compare different methods in 3 different sequencing tasks: finding the correct sequence of lectures, predicting the next lecture, and predicting the sequence of lectures. In the qualitative evaluation, we show some examples of the main topics and their transitions. We collected our dataset from real online courses using different MOOC platforms and in 3 different domains: Python, structural query language, and machine learning clustering algorithms. And the table here presents the statistic of the dataset. In this work, we use 75 of the dataset as a training set and 25 as test set, as we assume the sequence of lectures in the test set as the ground truth sequence. We use 4 measures: Kendall Tau. It is information retrieval measure that captures the correlation between 2 ranked lists, where 1 means perfect match and -1 means total mismatch. We also use Livingston normalized similarity, and it is the opposite of Livingston normalized distance that measures the minimum number of edits, for example, insertion, deletion, or substitution, required to transform the predicted sequence to the ground truth sequence. So here, higher is better. Directed bigram precision and undirected bigram precision capture the correctness of the transition between adjacent lectures, where in the directed precision we take into consideration the direction, while in the undirected one we ignore the direction. So the first task, which is finding the correct sequence, is just using a permutation method to find the correct sequence. When the courses have large number of lectures, it is invisible to find all ordering of lectures. Therefore, when the number of permutations exceeds 500, we randomly permutated 500 possible ordering of lectures as candidates. We ran the experiment 20 times for each method and recorded the average results. So you can notice here from the table that PCK-means has the highest score in Kendall-Taus and Livingston normalized similarity in all data set, which indicate that PCK-means has chosen the sequence that are very correlated to the ground truth sequence and need minimal edit to be transformed to the ground sequence. However, PCK-mean only outperforms other models in the directed and undirected bigram precision in the Python dataset. So indicating that it's sometimes not able to capture the sequence between adjacent lectures. For the second task, which is predicting the next lecture, each model predicts the next lecture given a sequence of lectures. We varied the length of the given sequence starting from 1. As STRTM and hidden Markov mixture model are based on hidden Markov model, we utilize here the Viterbi algorithm to find the most probable sequence of hidden states or topic that generated the lecture in the given sequence, and then greedily choose the next probable lecture in the sequence. Hidden Markov mixture model achieves the highest accuracy in all data set, and using Viterbi algorithm along with the learned topic transition helps in capturing the most probable hidden state or topic that generate the given sequence of lectures. While STRTM also uses Viterbi algorithm similar to hidden Markov mixture model, its accuracy score were far less than hidden Markov mixture model. We think the main reason for that due to the performance of the learned topic transitions, as we will see later. In the third task, predicting the sequence, each method needs to find the whole sequence of given lectures where the first lecture in the sequence is given. As this task is considered the most challenging task, it's clear that there is no winning method. For the directed and undirected bigram precision, all methods have comparable result except mixture of unigram language model. The reason is that mixture of unigram language model sometimes cannot complete the whole sequence because it only uses the greedy method, which cannot complete the sequence in the cases of the absence of the topic transitions required to sequence courses in the dataset. So in addition to quantitatively comparing the method, we try to qualitatively evaluate the results by examining the generated sequence of each method. In general, we found two common behaviors shared by all methods. First, all methods prefer self-transition when they pick the next lecture in the sequence, and all methods cannot sequence lectures that belong to the same topic. We also extracted some examples of the topic transition maps. We show examples from the Python dataset. And we can notice here PCK-mean have extracted 11 useful topics with 2 topics that have unclear word distribution and cannot be mapped to any useful topics. And PCK-mean has the best word distribution that clearly explain each topic. Mixture of unigram language model has modeled 10 meaningful topics with 3 topics form noise and cannot be mapped to any topics. Hidden Markov mixture model captures 9 topics with 4 unclear topics that cannot be mapped to any phrase. Finally, STRTM captures 9 topics with 4 unclear topics that cannot be mapped to any phrase, and STRTM has the lowest performance in the clarity of the word distributions. In this paper, we introduced the topic transition map, which is a general structure that models the different ways of how instructors organize topics in order to construct the study plan of their courses. And we'll investigate 4 different methods to construct the topic transition map: PCK-means, mixture of unigram language model, hidden Markov mixture model, and STRTM. And our evaluation reveals that PCK-mean achieves the highest performance in determining the correct sequence of lectures. Hidden Markov mixture model outperform other methods in the task of predicting the next lectures. And all methods capture useful topics with clear word distribution, with PCK-mean has extracted more meaningful topic with the best word distributions. So this is all what I have, and thank you.